is a voltage-based detection method for lightning discharges at distribution networks, presented by Lívia Fonseca Ribeiro. Lívia Fonseca Ribeiro was born in Belo Horizonte, Brazil. She holds a master's degree in electrical engineering in the field of electrical energy systems from Federal University of Santa Catarina in 2020. She graduated from the Federal Center of Technological Education of Minas Gerais in 2017. In 2014, she was an exchange student for over a year at the Brazilian government program at San Diego State University in the United States. In Chicago, she was a researcher for a group at Illinois Institute of Technology in 2015. She currently works as a project manager at Rendimento Engenharia. Please go ahead, present.
Okay, can you hear me well?
Yes.
Okay. Hi everyone, my name is Lívia Fonseca Ribeiro. I'm glad to be here today, directly from Brazil, to present the article entitled by A Voltage-Based Detection Method for Lightning Discharges at Distribution Networks. It was written by me, Miguel Moreto, Arlan Bettiol, Douglas Figueiredo, and Igor Khairalla. Here we have the overview of this presentation. First of all, I will give you a brief introduction about issues due to the incidence of lightning discharges and distribution systems. Next, I will present the simulation model and the proposed detection scheme. After that, I will show all the testing and the results obtained from them. Finally, I will present the conclusions of this study, do some acknowledgements, and show the references consulted. This study deals with the incidence of lightning discharges and electrical power systems. It is the most frequent cause of overvoltage and power failure, which can damage equipment and interrupt the power supply. As a result, it can negatively affect the indicators of electrical power continuity and quality. Besides, it can cause high financial losses. Currently, no protective equipment is dedicated to deal with lightning discharge detection. So, power utilities struggle to provide explanations to the regulatory agencies regarding the interruption of energy supplies resulting from this natural phenomenon. The method proposed is not intended to be used as protection against lightning discharge, but rather as a post-operation diagnostic tool. A simulation model was proposed in order to simulate the incidence of a direct lightning discharge. The IEEE 34 bus feeder shown in Figure 1 was chosen as a test feeder. It was proposed in 1992 and is well known. This feeder has a nominal voltage of 24.9 kilovolts. The main branch measures approximately 57 kilometers with unbalanced loading. Lightning discharges have high frequency characteristics, differently from the level of the rated system frequency, which in Brazil is 60 Hertz. Therefore, each component model should be frequency dependent. The ATP-AMTP software was used to implement appropriated models of lightning discharges, line segments, pole insulators, surge arresters, grounding elements, and transformers. It is a short presentation, so I will not give details about these models, but all of them are referenced and well described in the article. The sampling frequency was 50,360 Hertz, and the data used corresponds to the local utilities procedures. Now I will present the proposed detection scheme. It is composed by 3 parts: filtering, transient detection, and fault classification. The voltages measured at the secondary of a 3-phase potential transformer and the distribution systems substation are the inputs of the filtering part. The filtering part is composed by part transform and wavelet transform. It aimed to condense the three-phase signal into just two, the direct and zero components. The discrete wavelet transform main goal is to separate rated frequency and disturbance by calculating the approximation and detail coefficients. The detail coefficients help to identify the presence of lightning discharge characteristics. The direct wavelet transform was implemented using family Dalbish-4 to obtain the detail coefficients of direct and zero components. Great results were obtained just using the first level of the composition. After that, we have the scheme second part, transient detection. The main purpose is to detect if any significant transient occurs. It is composed by the energy calculation and the establishment of an adaptive threshold. So for this, we calculate the energy of the detail coefficients of direct and zero components according to equations 7 and 8. The maximum and minimum energy values are collected from the energy first two cycles. Then adaptive thresholds are calculated by determining the maximum deviation value described by equation 9 and the rate of change acceptable on the system steady state described by equation 10. If both thresholds are surpassed, the time instant of the transient is identified. The signal is scanned from this instant to the end of the data, and the energy maximum values associated with the detail coefficient of the direct and zero components are identified. The last scheme part is the fault classification. It just makes the difference between the maximum points observed after the transient occurrence of the direct and zero components of energy. Whether this difference is over 100,000 means a direct lightning discharge has reached the distribution system. Some events were simulated to test the efficiency of the detection scheme to distinguish lightning strikes from them, such as low impedance faults, modeled as resistance at 3 branches, high impedance faults designed as an anti-parallel diode arrangement, lateral energizing and de-energizing performed by a switch on 818 branch, capacitor bank switching on and switching off performed by a switch of a capacitor bank power at 830 branch. In table 3, there is a summary of the simulated events characterizing their results by node, phase, transient occurrence, and lightning discharge detection. As we can see, events 1 through 9 are lightning discharges in different nodes and at the same phase, phase B. In all of them, the transient was identified by the scheme and the lightning discharges were detected. Events 10 through 19 have different characteristics from lightning discharge. Their results show that the transient occurred and their cause are in the lightning discharges. Now I will show results from the first event of the summary, which were a lightning discharge over phase B and node 808. Figure 10 shows the three-phase substation voltages measured at the secondary of the potential transformer. Although the discharge occurred in phase B, all others were directly affected due to the mutual coupling between phases. We noticed that before and after the transient, the voltages have the same behavior, and the amplitude peak under the influence of the lightning is expressively high, over 6,000. In figure 11, there are the results of part transform. Even under steady state, the direct component shown an oscillatory behavior, and the zero component was approximately null. That reflects the unbalanced load feeder characteristic. The direct component was oscillated with peak value approximately 115 volts, which is the standard voltage of potential transformers. And the discharge incidence reflect in the systems is observed in the results of the zero component. The maximum value measured for zero component was nearly 5.9 kilovolts, and direct amplitude is still at the same level as before. In figure 12, there are the voltage wavelet decompositions of the components direct and zero. The detail coefficient amplitude related to component zero is much larger than that obtained for the direct component. The calculated energy for the detail coefficients are shown in figure 13 with the logarithmic scale. The magnitude order of peak energy of the zero and the direct component have great difference. So this paper presents a detailed simulation model of the IEEE 34 bus test feeder suitable for lightning discharge studies. The detection scheme proposed significantly simplifies the task of analyzing the cause of shutdowns and damaging transients in an overhead distribution network due to a direct atmospheric discharge. In conclusion, the results demonstrate that lightning discharge detection at the substation is possible without the need for expensive and complex data acquisition systems, just measuring voltage signals. We would like to thank Celesc Distribuição and CAPS for their financial support. And here we have all the consulted references. Thank you all for your attention.
Thank you very much for this presentation. Now it's time for questions. Any questions in the Q&A? Questions? There are no questions. So I do not see any questions in the Q&A for the moment. So I guess we should proceed. I will check again. So I guess we can proceed with, there are no questions. So I guess we can proceed with the next paper. So thank you very much.